course is convexity and duality in optimization problems arising in microeconomic theory. The theories I'm going to present here are rather classical in economics, specifically in microeconomics, but the treatment I'm going to make is more mathematical than is usually presented in courses on advanced microeconomics. And some of the results I will present are refinements of the results you can find in the literature. But overall, the theory is rather classic, I mean, most of it. It's microeconomics, but with the emphasis on the convexity aspects. Okay? So we will see the crucial role that convexity and generalized convexity plays in economic theory, in particularly in microeconomics. Well, you know, there is microeconomics and macroeconomics. Microeconomics deals with the behavior of individual agents, consumers, firms, while macroeconomics deals with, let's say, countries or much larger organizations. Well, so here we are dealing with microeconomic theory, and I will basically consider the main two parts of the theory, which are producer theory and consumer theory. Okay, and we are going to start with production, with producer theory. I will try to make the course as self-contained as possible, and in fact, we are not going to use very sophisticated mathematics. So I think it should be understandable to everybody. If something is unclear, will probably be because you are not used to the notation or to the terminology or for whatever other reason. But I will be very grateful to you if you interrupt me anytime you need some additional explanations. Okay, I would like to have some feedback with you as much as possible. Okay, so please feel free to interrupt me at any time. Well, so let us start with production theory, producer theory, and we are going to start with the cost function associated with a production function. So we are in a production environment in which there are inputs doesn't work. Before starting, I should tell you that most of my presentation is based on this book. Generalized concavity. By 4 authors: Averill, Dewar, Scheibel, and Zhang. It's an old book from the early 80s, but there have been several editions after that. The authors are, Averill was or is an optimizer, they were an economist. Scheibel was a good friend of mine. He passed away several years ago, unfortunately. And well, so this is the book I am going to follow mostly. But there are many more things in that book beyond the contents of my course. Okay, so we consider an economy in which there are n inputs. Resources, inputs are, I don't know, raw materials, labor, capital, which are necessary to produce something. And there are several inputs, but only one output. Okay, a more realistic situation is when there are several outputs. And the theory exists. In fact, an extension of what I will present here, but technically is much more complicated, is in a paper of mine. I can give you a copy to those of you who are interested, with my co-author Abelardo Jordan, a former PhD student of mine from Peru. So we have this joint paper with the title Duality between multi-output production, correspondences, and cost functions. This appeared in the journal Set Value and Variational Analysis. Analysis 2021. So in this paper, we basically did what I'm going to present, but in the multi-output context. But it's not so difficult to make this extension, but of course, it's more complicated. Here I'm about to introduce the production function, but in that general context, we need to deal with correspondences, set valued mappings. But the treatment is basically the same. It would be a little effort to present my results in this much more general concept. I repeat, I have an electronic copy of this paper. Whoever is interested, just ask me and I will send the file. Okay, then so we consider the input space which is R plus N. R plus is the non-negative half line. Okay, so a vector in R plus N is a vector with components x1, xn, all of them non-negative. Which mean the amount of each input that is used in production. We are using x1 units of input 1, x2 units of input 2, etc. And with these inputs, we produce some amount of one output. Okay? And this, mathematically, this is represented by a so-called production function. production function is a function which I will denote by capital F from the input space into the non-negative reals, which assigns to every input vector the largest amount of output f of x1 xn that can be produced by means of these inputs. Okay, this is a production function. It represents the available technology to the producer. Okay, so this is the basic concept we are going to deal with. And now, associated with a production function, there is the so-called cost function. If you want, you can write C sub f if you want to stress that it is the cost function associated with the production function f. And this production function is defined on the Cartesian product of R plus with R plus n, R plus n into the non-negative reals union plus infinity. Well, first, R plus n, R plus is the set of strictly positive real numbers. And here we are considering strictly positive numbers because they will be prices. Nothing is for free, as you know. Okay? So, an element in R plus n is a vector P1, Pn of strictly positive numbers, which we will interpret as prices. P1 is the price of input 1. P2 is the price of input 2, etc. And the producer is behaving competitively, which means that he or she is taking the prices as given. Okay? Well, then the cost function
PI per unit cost.
sorry?
In this PI per unit cost for X1 per unit.
PI is the price, is the unit cost of input I. This doesn't work very well, so if or if not, it will be better to use the chop. Well, then, so I am to define the cost function. It has two arguments. One in R plus, which I'm going to call Y, to be interpreted as the output level. The amount of output we want to produce. And the second argument is a price vector. an element in R plus plus n. And it, sorry, associates to this pair the smallest amount of money that the producer has to spend under these prices, represented by P, in order to be able to produce at least Y. Okay, so formally, this is the infimum of the inner product pre-Y subject to f of x greater than or equal to y. So here py is, as I said, the inner product, sorry, px. This doesn't make any sense because y is a scalar. So px is p1 x1 plus pn xn. Means if I use the input vector x under these prices, this is what I have to pay. to obtain those inputs. But my choice of inputs should be compatible with y. Okay, I should be able to produce, with x, thank you, with x, I can produce f of x, and I want to produce at least y. Okay? So what is the smallest cost I have to pay to produce y or more under the prices represented by vector p? This is this, given by this expression. Do you agree? So we have to minimize the cost subject to the feasibility of y. Okay? That's the idea, very simple. Then, I'm not making any assumption on the production function f. In a minute, I will make just one technical assumption for convenience. But f is any production function. Any function which may be even absurd from an economic point of view. You may be considering a function in which you use more inputs and you produce less. We can consider this mathematically, but later on we will see which are the reasonable properties that a production function must satisfy, and this will not be dictated by the economic intuition, although it will agree with the economic intuition, but mathematics will tell us which are the regularity conditions that a production function should satisfy. Okay, but for the moment, f is any function. And because it is any function, I don't know if the infimum is attained or not. But I want it to be attained. So I'm going to make an assumption. The only assumption that I'm going to use for production function for the time being, namely that f is upper semi-continuous.
So that the constraint set is closed.
Sorry?
So that the constraint set is closed.
So that the constraint set is closed. I needed the assumption. So I define upper semi-continuity in the following way. There are two equivalent ways, and I'm going to prove the equivalent of these two alternative definitions. F is upper semi-continuous means that the upper level sets of f, u stands for upper level set of f at the level y, is by definition this set. So upper semi-continuity simply means that these sets are closed. Okay? Then, as you said, this means that the feasible set in this optimization problem is closed. Good, but this is the only assumption, just for technical needs. One first observation, rather easy to prove, but I will make the proof because, as I said, I want to have my course as self-contained as possible, is that a function f is upper semi-continuous if and only if the hypograph of f defined as the set of pairs xy in R plus n close R, such that f of x greater than or equal to y is closed. At first sight, you may be thinking that I am saying the same here and there, but I'm not, because here we are in R plus n, and here we are in M plus n product R. So it's not the same, but it's easy to prove, as you will see now, that these two conditions are equivalent. I mean, to see geometrically the difference, suppose you have a function with this graph. What are the upper level sets? You fix a level y, and then you look at the points in which this level is higher. So it will be all this half line together with this interval, okay, and this half line. The set of points where the function takes a value larger than or equal to the given level y. As you say, this is in the domain of the function. The hypograph is something very different. The hypograph is everything which is below the graph of the function. It's in a different space. Okay? If I write here equality instead of inequality, then this is the classical definition of the graph of the function. But here is, what is below the function. Okay. Well, now let us prove this equivalence, and the obvious implication is from right to left. This is here.
So maybe you want to mean that this capital F is that F, right? Maybe.
This is an arbitrary function.
So in a statement, then I guess you wanted to write x n, not r plus.
No, because I am just considering.
The same.
I'm just considering functions defined on R plus n. But of course, I mean, you can define this in an arbitrary topological space. For the notion of upper semi-continuity is okay. Yes. Then, so let's prove that F is upper semi-continuous, assuming that the hypograph is closed. So we have to prove that all the upper level sets are closed. So let's fix a level. And consider a sequence of points in the corresponding upper level set converging to some point, and to prove closeness of this level set, we have to prove that x belongs to that level set 2. Okay? But then, this condition means, by the definition of upper level set, that f of xk is greater than or equal to y. But this means that the pair xk y is in the hypograph of f. And because xk tends to x, this pair tends to xy. And because we are assuming that the hypograph is closed, then this limit point is in the hypograph of f, which means that f of x is greater than or equal to y, which means that x belongs to the upper level set of f corresponding to level y. So it's really a trivial exercise. In the opposite direction, it's also very easy, but slightly, only slightly more complicated. Excuse me?
Is there restriction on y?
No, in principle not. I mean, I mean, if y is negative or even 0, then this is the whole space, because f only takes non-negative values. I mean, you could redefine in our context the upper level sets with only non-negative y. But for this definition, I prefer to consider every I in R, although you are absolutely right, there would be no difference if I consider only this, okay? Because if y is negative, then this is the whole space, which is closed. Thank you. Okay, so now for the opposite, for the converse implication, now we are assuming that f is upper semi-continuous, meaning that all the upper level sets are closed, and we have to prove that the hypograph is closed. As you can imagine, it's slightly more complicated. Why? Because now we are increasing the dimension. In this implication, we were going from Rn plus 1 to Rn. Now we are increasing the dimension. This explains the very little extra complication in the proof. So now, assuming that all upper level sets are closed, to prove that the hypograph is closed, we consider a sequence of points in the hypograph assume that it converges to some point, and then we have to prove that this point is also in the hypograph. Okay? Now we consider two cases which would be unnecessary to distinguish with your proposed redefinition. Okay? The first case is when y is less than or equal to 0, a case that you rightfully wanted to exclude. Then, of course, in this case, f of x is greater than or equal to 0 because f only takes non-negative values. This is in turn greater than or equal to y. So X belongs to the upper level set of F corresponding to Y. So what we are proving now, not simply XY is in the hypograph. Oh my God. Of F. So in the case is easy. Now consider the case in which Y is positive. Now it comes the little extra work. We have to consider an intermediate number, arbitrary intermediate number, Y prime. And then, because Yk converges to Y, and Y prime is strictly smaller, then for K large enough, Xk will be, Yk will be strictly larger than Y prime for every K large enough. Okay? Then since we have Xk, Yk belongs to the hypograph of F, we have F of Xk greater than or equal to Yk, which is strictly greater than Y prime. And this means that Xk belongs to the upper level set of F corresponding to the level Y prime. Okay? Then, since Xk converges to X, and we are assuming now that F is upper semi-continuous, which means that all the upper level sets are closed, then the limit of Xk is in U of Fy prime. What does it mean? That F of X is greater than or equal to Y prime. But Y prime was any number, an arbitrary number smaller than Y. So if F of X is greater than or equal to any number strictly smaller than Y, it is also greater than or equal to Y. That's very easy to prove. If you want an argument I don't like because it's too much for this elementary proof, but is make Y prime tend to Y. And then this inequality yields Fx greater than or equal to Y, which we had to prove, no? Because this means that Xy is in the hypograph of F, thus proving that the hypograph of F is closed. So as I announced, it's a very simple proof. Okay, so this is the only assumption we are going to consider. But under this assumption will allow us to replace here infimum with minimum. Be careful. This assumption simply means that the feasible set in this problem is closed. But a linear function over a closed set does not necessarily attain a minimum. Consider, for instance, a hyperbola which is a closed set, and consider the linear function y. The infimum is 0, but it's not attained. Okay, so it's not enough. So what is so which are the extra conditions that assure us that the infimum is attained? One is that there are here constraints which are implicit. There is, which ones? That x is non-negative. This is implicit in this expression because I'm writing f of x, and f is only defined on r plus n. So all our variables are non-negative. And what else? And all the prices here are strictly positive. Okay? Then, assume for a moment that this is feasible. Assume that there exists x, let's say x bar, such that f of x bar is greater than or equal to y. This does not necessarily exist. Y may be too much. We may be wanting to produce too much. Okay, but suppose for a moment that there is such x bar. Then nothing changes if you add this extra constraint. I mean, on top of the original constraint, I add this extra constraint, and do you agree that it doesn't change the optimal value? Because we are minimizing p of x. Here we are simply imposing to be below a feasible value. If we are minimizing, this does not make any extra constraint. Do you agree or not? Feel free to disagree. I am inviting you to disagree. I think it's clear, but may not be clear to you. Well, if you say
Extra constant of x bar is smaller than the previous value.
yes, but in spite of being smaller, the optimal value doesn't change. That's the point that you have to agree. Okay? Because if you are minimizing, you will end up with a value satisfying this constraint. So this constraint is somehow irrelevant. But why is it convenient? Because if we impose this extra constraint, then the feasible set becomes compact. It was already closed, but now it's also bounded. Why? Because we have this constraint means sum of pi xi less than or equal to sum of pi xi bar. And of course, everything here is non-negative. So for each individual term, you have this inequality, which means every variable is less than or equal to 1 over p I sum of pi, well, I should use a different, let's say j, okay? Sum of pi x bar I. So each variable is bounded from below by 0 and from above. This defines a closed set, these two. And now we have compactness because we also have boundedness. Means the infimum is attained. So from now on, I am free to write minimum because it is attained instead of infimum. But be careful. To make this step, I needed to assume the existence of this X bar. So why, if such X bar doesn't exist, means I want to produce too much, something which is beyond my technology. This means that this set is empty. And then I am minimizing over the empty set. And for this reason, it's a pity that I erased it. For this reason, I needed to add plus infinity here. The cost function may take the value plus infinity. I suppose I wrote it correctly, no? When I define. Why? Because if this is the empty set, the infimum over the empty set is plus infinity. Many people used to say, but I don't like, that this is by convention. Then we will, you may find it even maybe in my papers with co-authors, but then it was the fault of the co-author and I didn't want to argue with him. They say the infimum over the empty set is plus infinity by convention. Why by convention? By definition of infimum. The infimum is the largest upper bound. For the empty set, everything is an upper bound. So the largest upper bound is plus infinity. Why do you need a convention? It's the definition, to me. Okay, so this expression is wrong when this set is empty. But we will keep this notation with the convention, now it is a convention, that the minimum over the empty set is plus infinity. This is a minimum which is not attained. Okay, but in order to avoid distinction between the feasible set is non-empty or is empty, then I simply adopt this convention, and of course, minimum in this case doesn't mean that it is attained. Okay, as you like. Okay, this is a good time to make a break because now I will start one of the main results of this first part.